Welcome to week 9 on radicals. We're in the home stretch now. Radicals, I think, is going to be a little bit easier of a concept, and these are the things that we are going to cover this week. We need to know a little bit about our terminology. We need to know the laws of radicals. We need to figure out how to simplify them, how to solve the radical equations, and then an application problem using Pythagorean theorem. That is the goal for this week. This is a radical sign, also known as a square root. Or the radical symbol, or the square root sign. It's going to be used to cancel out squares. Thus, it's called a square root. Now, a radical doesn't exist by itself. You have to have a number underneath here. The number underneath is called the radicand. The radicand can, the radicand can. Whenever you see a radical, this is the inverse operation of squaring. Everything that we do in math land, we learn how to undo it. We first learned how to add, and then we learned take away. We learn multiplication, then we learn division. Well, we've always kind of learned the square, but we never really learned how to undo it. And that's what we get to do this week. So when I see something like this, it's called the square root of 16. We need to remember that the key thing that this is not is division. We are not ever taking that radicand and dividing it by 2. We have other symbols to mean that. We would not use this ugly little thing. It kind of looks like a long division sign with a boot on the end. That's exactly what's happening. We're wanting to boot out squares, which is why it's called a square root. Okay? So when we see something like this, the square root of 16, we're asking ourselves, what number times, and this is key, itself is 16? The answer to that is the answer to what is the simplification of the square root of 16. So the square root of 16 we know is 4 times 4, so the square root of 16 is 4. Now we've used the square root symbol because the square root symbol is telling us to answer this question. Because we answered the question, we used the symbol, which means that it's not there anymore, and the answer is simply 4. Now 16 was a nice one because it's a perfect square. We probably want to get fairly familiar with our perfect squares. We may be fairly familiar with a lot of them from our factoring chapter. That was chapter 5, week 6, in which we had the difference of perfect squares was one of the things that we factored. And so our perfect squares are 1, one's a perfect everything, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, 225, 256, x squared, etc. That would be your first 16. Those are probably the ones that we would be using the most often. So make a list of those so that you are familiar with them, so that you can recognize your perfect squares in case it comes up underneath a radical. So remember, a radical or the square root is just canceling out the idea of a square. So we're finding out what number times itself would give us that. With anything in math land, we have laws to go along with it so that we can follow the correct rules and have a joyful visit in math land. We have 2 radical laws. The first is that of a product. So if I have the square root of a product, remember a product means multiplication. So I have 2 numbers being multiplied together underneath my radical. The product law allows me to separate those into 2 radicals that are still being multiplied. This helps us with some simplification that we'll show you in just a bit. Now, if there's a law about a product in Mathland. Because division is really multiplying by a reciprocal, division's the same thing as a product. If there's a law on the product, there has to be a quotient law as well. The quotient law is very similar. If I have a quotient, we like to call them fractions, underneath the radical, we can write that as two separate radicals. The a stays in the numerator, the b stays in the denominator. Okay. Now, technically in Mathland, it's not simplified to have a radical in the denominator, so we're always hoping that that b value is a perfect square. If it's not, we'd have to go through a technique called rationalizing the denominator. This might be important for you to go through in your book because there's definitely, I think, one problem either on the quiz or on the final exam that talks about this. So you definitely want to review rationalizing the denominator from your textbook. Rationalizing the denominator is found on page 645 in your book, and then a more complicated method for a little bit harder types of rationalizing the denominator is on page 655. It's just multiplying top and bottom by a 1 in order to get rid of the radical in the denominator. We're not going to focus on that here as it's just one problem. But the quotient law and the product law will help us do some simplifying. That comes up next. Simplifying radicals. Now it's easy to simplify radicals if the radicand, that number underneath the radical, is a perfect square. But what happens if it's not? What if I have the square root of 75? Now we could just plug that into our calculator using a square root button, but once we do that, we realize that the entire calculator's display screen is completely covered with numbers. That's because radicals are under the form of an irrational number. That means that they cannot, ir means not, be written as a ratio or a fraction. In other words, it's a non-repeating, non-terminating decimal, that, one of those that goes on forever and ever and ever with no pattern to it. We don't necessarily want a decimal approximation unless the directions state, find the decimal approximation. We want exact answers. Exact answers means that you might have a radical still in your answer, and that's okay. Okay? But just like with fractions, we want to make sure that our radical is as simplified as possible. In other words, to compare with a fraction, we would not leave a fraction as 3/6. You would automatically reduce it to 1/2. Likewise, with a radical, we want to simplify, which means that if there's a perfect square factor, we want to take that out. We can do that and do the simplification because of that product law that we just talked about. So we don't have a product, though, in this problem. We just have the number 75. Well, what I want to do is rewrite 75 as a product. What times what is 75? And I can go through and I can think, well, 5 times 15 is 75. However, I don't want to choose this combination. Do you know why? It goes back to our list of perfect squares. 5 nor 15 are on our list of perfect squares. That's not going to help us. We want one of the factors to be a perfect square, one of these. So going back to our problem, we say, okay, well, 75, hey, if I have 75 cents in my pocket, it means I have 3/4. Quarter, or 25, is a perfect square. So that's the one I want to use because it has a perfect square, and let's face it, 25 is a fairly large perfect square. So I'm going to rewrite 75, or the square root of 75, as the square root of, don't lose that radical just because you're not understanding it, 25 times 3. Now I've always put my perfect square first. It's easier for me to see things, but it's not a requirement. So 25 times 3 is the same thing as 75. We still have the square root symbol because we have not used it yet. We can't just make it disappear. Okay? But now we can apply our product law of radicals. It says that if I have a product, I can write that as two separate radicals. So that's what I'm going to do. The square root of that is going to be equal to the square root of 25 times the square root of 3. Technically in this spot, the multiplication dot is not necessary. I'm using it to give myself a little extra space and to remind myself that I'm multiplying. Now that we have two separate radicals, we can go through and say, well, can I simplify those? Can I find the square root of 25? Is there a number times itself that gives me 25? We say, sure, there's 5. I use the square root symbol by asking myself what number times itself is 25. That answer is no longer underneath the radical because I've used that symbol. Is there some number times itself that gives me 3? No. To get 3, I have 1 times 3. That's it for integers. No ugly numbers. So I can't do anything with that. But it's still there. It's part of my problem. So it comes down. Now, because the 3 is underneath the radical, it's kind of like a letter, and you can tell that the 5 is not the same thing because the 5 is not underneath. So just as if we were writing 5x, I don't need to put the multiplication dot between the 5 and the square root of 3. It's assumed multiplication because they're mushed together. Just like if it was 5x, we assume it's 5 times whatever x is. So you do not need a multiplication dot here. Another thing to note, 5 is not underneath the radical. 3 is. You can't take a number that's not underneath the radical and multiply it times a number that is underneath the radical. So we can't end up with a 15 anywhere here. Only 5 times 3 is 15. This is 5 times the square root of 3, or the number that times itself gives us 3. So this is as far as we can go. This is simplified. So the square root of 75 is equivalent to 5 square roots of 3. Let's do another one. How about the square root of 72? Now the first thing I see with 72 is I remember that that is one from my multiplication tables. 8 times 9 is 72. And 9 happens to be one of my perfect squares. So I'm going to use that. Once again, I like to write my perfect square factor first, just so that when I break it into the two separate, it's already out in front. Now, because I rewrote 72 as a product, I can separate those into two separate radicals. So that's the square root of 9 times the square root of 8. Now the square root of 9 I can simplify. That's 3. And I can't, can I simplify the square root of 8? 8 is 4 times 2. So I can go further with the square root of 8. The square root of 8 I can rewrite as 4 times 2. Why do I want to do that? 4 is a perfect square. Well, once again, I can keep going and say, okay, well that 3 just comes along for the ride. I'm not doing anything with that. But I can rewrite this, now that it's a product, as two separate radicals. And now I see that I have another perfect square, so I can simplify that. Square root of 4, what number times itself as 4 would be 2. Now I can't just put a 2 down here because now it looks like the number 32. Now I have to put my multiplication dot back in. I can't simplify the square root of 2, so I leave that as the square root of 2. There is no number times itself that gives me 2. 1 and 1 adds to 2 but multiplies to 1. Be careful there. 2 is just 1 times 2. Neither of those are a perfect square that you can simplify. Okay? 3 times 2 now, both of these numbers are not underneath the radical, so we can multiply those. Remember, you are always multiplying. It's all about multiplication. So our answer here is 6 square roots of 2. So the square root of 72 is equal to 6 square roots of 2. Why do I always put that perfect square in front? Well, if I had chosen to put it in the back instead, it looks a little confusing. We might have to use parentheses or a multiplication dot, and it just gets messy. We don't like that. Always put the rational number in front of the irrational number. Rational numbers are more important anyway. Wow, 2 steps to simplifying that one. We first found 9 times 8, and 9's a perfect square, and we simplified that, but then we remembered that there's a perfect square in 8. Was there a way that I could have done this faster? Could I have done this in 1 step and not 2? Well, of course. That's why I asked the question. We just went to 72 and thought, oh, 9 times 8, because that's part of our multiplication tables. But if we had taken a little extra time, we could go through and find out the other factorizations of 72. And if we had done that, we would have gone through and said, oh, well, it's even, so 2 goes in there. Oh, 36 times. 36 is one of my perfect squares. And it's much larger than the 9. So if you want to do simplify your square roots in 1 step and not 2 steps, you're going to have to think about the largest perfect square factor, not the first one that comes to mind. So let me show you how that would work. If I had done the square root of 72 is equal to the square root of 36 times 2. And remember, make sure that you use your calculator to double check this. Sometimes our brains work in funny ways and it doesn't split things quite right. So now we can write it as 2 separate radicals. And the square root of 36, what number times itself is 36? Oh, that's 6. And I can't simplify the square root of 2. I got the same answer in 1 step as opposed to the 2 steps over here when we had to break it down here and then break it down again. Either way, we got the same answer of 6 square roots of 2. It just matters how fast we get there. So there's more than one way. You don't have to always find the largest perfect square. But if we take a little extra time for our factorizations, we'll find the perfect square a little bit faster. Now, what about variables? What's the square root of x squared? Well, the square root of x squared, because we have a square and a square root, they cancel each other out, and you end up with just an x. What number times itself gives me x squared? Well, x times itself gives me x squared, because that's the whole definition of it. Does that make sense to us? Let's go back to that first one, square root of 16. 16 we could also write as 4 squared. A square and a square root are the inverse operations. They cancel each other out, and the base number is your answer. The base number becomes your answer. So then what happens if I have the square root of x cubed? Well, x cubed is made up of x squared times x. Remember the laws of exponents from chapter 4. When multiplying like base numbers, you add your exponents. 2 plus, if there's nothing up there, there's always 1. That's the god of math land. 2 plus 1 is 3. And now you can separate them into, oopsie. Try to refrain from what I just did there. Don't make your square root symbol too long that it overwhelms the rest of the problem. When you're typing in the equation editor, it means that you're going to have to make sure that you click outside the radical when you're done typing it, or if you're not sure if you can do it that way because it's a little bit futzy, arrow to the right. If you click the right arrow on the equation editor, you'll get out from underneath the radical and that bar won't continue across. That would be the correct notation. We always want to work on correct notation. So, how does that sum that up? If I have the square root of x to the 7th, well, that's x squared, x squared, x squared, and an x. Well, since a square and a square root cancel each other, instead of doing all this extra work, okay, so every x squared is an x, so we'd end up with x cubed and 1's left underneath. This is the shortcut. When you have a variable raised to an exponent, because this is a square root, we're looking for pairs. I want to know how many pairs or how many 2's go into 7. There are three pairs go into 7. That's the exponent on the x that's outside the radical. Now there's still 1 left over because 7's an odd number. So the remainder goes underneath. And remember, when we divide by 2, you either have a remainder of 1 or no remainder at all. So if you have a variable to an exponent, just take that exponent and divide it by 2. That's going to be the exponent on your variable outside the radical. If you have a remainder, it's still underneath the radical. If you don't have a remainder, you don't have a radical anymore. Solving radical equations. Solving radical equations has 4 steps to it. Now I know as students we like to always skip the last step, but actually in this case it's the most important step. So don't skip any of them when we're solving radical equations. The first step in solving radical equations is to isolate the radical. So if you have a square root, you want it all by itself on one side of the equal sign, everything else on the other side. It does not matter if the radicand is just a single term or if it's 2 terms or 3 terms. Still, that entire radical expression has to stay on one side. Remember, you can't change over if you do have 2 terms underneath the radical. Keep that in mind. We'll talk about that in one of the examples. Okay, so isolate the radical. Step number 2, well, the reason that we can't solve a radical equation is because of the stupid radical. We don't understand that exactly. So we're going to get rid of it. A radical is a square root. It cancels out a square, which means that a square cancels out a square root. They cancel each other. So the second step is to square sides. Square both sides. You cannot square individual terms. Whether it's underneath the radical or outside, it's squaring both sides of your equal sign. After you square both sides, you'll get rid of the radical, and so now you have an equation that you can solve. The remaining equation will either be linear, which means that you just have x to the first, and you get x on one side and everything else on the other side. Or it might be quadratic, meaning that you have an x squared. That's what we did back a couple weeks ago. You'd have to then set the equation equal to 0, factor the trinomial, set your factors equal to 0, and solve. Okay, so that same procedure of solving that we did in the chapter on factoring keeps coming back. It's using that zero product property, my favorite property. Okay? And then after you solve, though, here is the key. The one thing that we don't like to do, but we have to do with radicals, is check the answer. We might get 2 answers, and maybe one of them doesn't check. Maybe neither of them checks, because maybe we did some illegal math. When we squared, maybe there was a negative that we introduced. Okay? We have to take that into consideration. So those are your 4 steps for solving a radical equation. Let's go through one. Here's our equation. 3 plus the square root of the quantity x minus 1 equals 5. Remember, you're taking the square root of this entire quantity. Our laws said if we had multiplication or division, we can separate these. We don't have that. We have subtraction, which means that we cannot separate the radical, or the radicand. We can't take away that 1 from the x. A radical is is an assumed set of parentheses. What's underneath the radical has to be done first, and then you take the square root of that when you are simplifying. Because we don't know what x is, we can't take 1 away from it, so we can't proceed in that fashion. That's why we have to do other things to solve this equation. So step number 1, isolate the radical. Is the radical, which is this entire portion, the square root of x minus 1, is that by itself? No, we have this 3 over here. So the first thing that we have to do is move the 3 to the other side. To move from one side of the equal sign to the other, we do inverse operations. It's a positive 3. The inverse of a positive 3 is a negative 3, or subtracting 3. So you do the same thing to both sides. 3 minus 3 cancels. You're left with the square root of x minus 1 is equal to 2. So that was step number 1, isolate the radical. Step number 2, now that the radical is isolated, we want to get rid of it. So in order to do that, we square. When we square both sides. So this entire side gets squared, this entire side gets squared. The square cancels with the square root. That's why we do it. Those are inverse operations of each other. They cancel each other out. So a square cancels with the square root, leaving the radicand behind. And on the other side, 2 times itself is 4. Now we have a linear equation that we can solve. We solve this by, once again, getting your variable by itself. It's x minus 1. To cancel out subtracting, we add 1. Whatever you do to one side, you do the same operation to the other side. So we get x is equal to 5. Let's see here. This was step 2. This was step 3. Now the key step. We have to check our answers. So now that we know that our answer is x, the value of x is 5, we go back into the original problem before we do anything else to it. That's where you have to check and simplify. See if the left side equals the right side. So I'm just going to rewrite that equation down here. And now I know that x is 5, so where there's an x here, I'm just going to replace that with 5. Just replacing, I know that x is the same thing as 5, so where there's an x, I replace it with 5. Now we simplify using our correct order of operations. Like I said before, a radical is like an assumed set of parentheses, so we have to simplify what's inside here first. 5 minus 1 is 4. You still have the radical sign. We haven't done anything with that. Now that it's just a single value under there, I can simplify. What is the square root of 4? What number times itself is 4? Well, that's 2. And now you can simplify 3 plus 2. Yep, that's 5. 5 equals 5. It checks. So this is just the check, telling us that this is our answer, and our answer works. Let's try another. Here's another problem. The square root of the quantity x minus 3 is equal to x minus 9. Now fortunately for this problem, our radical is already isolated. Square root of x minus 3 is already by itself on the left side. Doesn't matter which side, as long as it's all by itself on one side. So now I can go straight to step 2. Square both sides. So I'm squaring this side, and I'm squaring this side. On the left side, the square and the square root cancel each other, as those are inverse operations, leaving us with just the radicand of x minus 3. On the right side, however, this is the key thing to remember. Very important to remember this. You cannot bring a square inside with addition or subtraction. Our exponent laws from chapter 4 say if there is multiplication or division, you can bring an exponent inside, not addition or subtraction. You need to remember what the square means. The square is on the outside of the parentheses, meaning what's inside the parentheses is taken times itself. So to write that out, it's really indicating that we're taking x minus 9 times x minus 9. And in order to multiply polynomials, you take each term of the first set and multiply it to every term in the second. We also know that as the FOIL method. So you will need to do that in your next step. So if you have an extra variable here, you're going to have to FOIL. Your outside was a negative 9x, your inside is a negative 9x. 9 and 9 makes a negative 18. Negative 9 times a negative 9 is a positive 81. So now we have an x squared. In order to solve this, we have to have the equation set equal to 0. You cannot use the zero product property if your equation is not equal to 0. So our next step is to subtract x. And we may as well do two steps in one. We will also add the 3. Now, be careful here. We like to just get a little bit lazy. You need to remember, we started with an equation. This is a balanced. The left side equals the right side. Since we have this balance, you still have the balance through the entire problem. So even though we cancel things out, they become 0. X minus x is 0. Negative 3 plus 3 is 0. You get 0 on that side. Don't lose the fact that you have two sides of an equal sign to represent this equation. Then the x squared, there was no terms like the x squared, so that comes down. Negative 18x minus x is a negative 19x. And 81 plus 3 is 84. Our next step is to factor. Still have the 0, because remember, the zero product property says I need to have a product or multiplication equal to 0. Fortunately, this is the easier kind. What times what is x squared? Well, that's going to be x and x. The positive 84 here tells me that both of my signs have to be the same. Since they have to add to a negative, they both have to be negative, because a negative times a negative will give me that positive. Now I need to think of factors of 84 that add up to 19. Well, the first thing I think of is the fact that I have an 84-inch couch, which is 7 feet. So 7 times 12 is 84. We don't call it a couch, we call it a Davenport, I guess. So 7 and 12 multiply to give me 84. Oh look, 7 and 12 ends up adding to 19. So 7 and 12 are the two numbers. So now we can use the zero product property, which states if I have two numbers multiplied together equal to 0, either x minus 7 equals 0 or the x minus 12 equals 0. Now we have two small linear equations that we should be able to solve. X minus 7, to get the x by itself, we add 7. Show all of these steps, because otherwise we have the tendency to say, oh, x is negative 7, and it's not, it's positive. Or, same thing over here, add the 12, x equals 12. So we have these two solutions. But wait, we're not done, because we have to check our answer. Let's go back into the original, always into the original. Okay. And let's check the x equals 7. So I'm just going to replace all 7s, or all x's with 7. So I have 7 minus 3 is equal to 7 minus 9. 7 minus 3 is 4. 7 minus 9 is a negative 2. What number times itself is 4? Well, that's 2. Does 2 equal negative 2? No. Bad guy, evil Lynn Skeletor, man in black hat, x equals 7 does not work. It doesn't check. Because when we find a square root, we're always looking for what they call the principal root, which is positive. So that one does not check. Let's check the 12 quickly before I run out of time. 12 minus 3 is equal to 12 minus 3 is 9. The square root of 9 is 3. 3 equals 3. That one checks. So x equals 12 is the only one that checks. X equals 7 does not check. It's called an extraneous solution. Extraneous solution, and does not check. That's why it's so important that you check all of your answers when solving radical equations. One or both may or may not check. One application problem is using the Pythagorean theorem. The Pythagorean theorem was named off of the Greek mathematician Pythagoras, who lived in the 6th century BC. Most likely he is not the one who came up with the Pythagorean theorem, but all of his followers and his followers' gave him all the credit. Not like in today's world where we give ourselves the credit. Here they always gave their teachers the credit. I know this because he taught me. Idea. The Pythagorean theorem is used only for right triangles. And it shows the relationship among the three sides of a right triangle. So it relates the three sides of the triangle. Now, what is a right triangle? Well, a right triangle is a triangle that has a right angle. What's a right angle? A right angle is a 90-degree angle. It's indicated by having a little square in it. That is a right angle. A right angle is a 90-degree angle. So we have three sides of this triangle. Two of the sides, the two sides that form the right angle, are called legs. Once again, the legs are the sides that form the right triangles. We don't really care which one is which, because of our formula it will not matter. The key is to know that the longest side, which is also the side always across from the 90-degree angle, that is called the hypotenuse. The hypotenuse. That is always the longest side. Always the side across from the right angle. Now, for our theorem, the Pythagorean theorem, there's a nice little formula to it. We simply call the legs A and B. Once again, it does not matter which one you call A and which one you call B. The key is that the hypotenuse is always side C. And what was discovered was that if you squared this side, which was essentially creating a square off of here, and if you squared this side, which essentially once again was making a square off of here, and you added those two together, every single time you had a right triangle, it equaled the C value if you made a square off of there. So simply put, without all that scary picture stuff, we simply say A squared plus B squared will equal C squared. That's why it does not matter which one's A and B, because you'll square them and then add. And remember, the order of addition does not matter. So this is Pythagorean's theorem. A squared plus B squared equals C squared. Now let's come up with a couple of examples. All right, say we have this triangle with one side on the left a 4 and the bottom is a 3, and then we have x, or unknown, for our other side. First thing we need to make sure that we do is identify the sides. What are we looking for? Do we have an A? Do we have a B? Do we have C? What was the difference again? A and B are going to be legs. The legs are the two perpendicular lines, the two lines that form the right angle. C is always the side furthest or across from the right angle and not touching it. So the hypotenuse is over here. So that's what we're solving for. That's what we don't know. In our formula of a squared plus b squared is equal to c squared, the hypotenuse is always c. So we don't know c. Does not matter what we apply, which we say is a or b for our legs. I'll just go in that direction. Now we replace the a. A is 4. Now the formula says to square that, so I have to put a square on that. Then we add, b is 3, and there's a square on that. And then that's going to be equal to, well, since I wrote an x over here, we'll replace the c with x. But that x, remember, is still squared. That's still part of the formula. So now we simplify this side. Well, in order to simplify, we do our order of operations. Please excuse my dear Aunt Sally, which says I have exponents first. The square, once again, tells me that I have two 4s that are being multiplied together. So 4 times 4 is 16. Remember, we never take a big number times a little number. That's bad. Then we go plus 3 times itself is 9, and that's going to equal x squared. Continuing on, we now just do our addition, so we have 25 is equal to x squared. Remember, when you're adding by 9, you can always add 10 and then take 1 away. So 16 plus 10 is 26, then take 1 away, and you get 25. Right? Well, that's all fine and dandy, but we're not done yet. 25 is what x squared is equal to. I don't want to know what x squared is, I want to know what x is. Now, remember, whenever we do anything in math land with an equation, we can't just move something from this side over to that side. We have to do the inverse operation, the operation that will cancel this. So some number squared is 25. Well, to cancel out a square, we square root. Whoopsie. If I square root one side, I have to square root the other side. So the square and the square root cancel on this side, leaving me with just my my base number of x. And on the other side, we say, well, what number times itself is 25? And we get 5. So my answer is x equals 5. That happens to be one of the special triangles. It's called the 3, 4, 5 triangle. It's the only one that has consecutive numbers like that complete the Pythagorean theorem. Hold it true. Construction workers use that a lot to make sure that they can form right angles. The ancient Egyptians, it shows that they used the 3, 4, 5 triangle. You measure 3 of any distance that you have, one direction, 4 the other, and when the corners match up to be 5, then you know you have a right triangle. And that's how they formed the pyramids, with perfect squares, a perfect 90-degree angle at all the corners on the base of the pyramids. They used Pythagorean's theorem, and the pyramids were built 2,000 years before our so-called Christ, BC. So 4,000 years ago. Kind of interesting. Let's do one more. Here I have one of my legs, and I don't know the other leg, but I do know that the hypotenuse is the square root of 3. Oh boy. So once again, if you need to identify it on your sheet, draw it all out. I know that a will be x, b will be 1, c will be the square root of 3. And now we plug it into our formula. Whenever we're using a formula, the proper thing is to write the formula down so that you don't make any little boo-boos. A we don't know, we called it x, so I'll replace it with x. B is 1, so I'm going to square that. And C is the square root of 3. All right, and we'll square that. Now we're still going to solve through, and in order to solve, we have to get rid of those squares. That's still going to be our first step. Can't do anything with an x squared. 1 squared, be careful here. 1 times itself a gazillion times is still 1. What happens when I square the square root of 3? Well, a square and a square root are inverse operations. They cancel each other, so I'm left with just the 3. Oh, that's not so bad. Now we solve. Or to solve, I have to get the variable by itself, so I'm subtracting 1. But I don't want to know what x squared is, I want to know what x is. So to cancel out a square, we take the square root. So x is equal to the square root of 2. Now, depending on what your directions state, you might want that as your answer, but if this says that you want to round, then you need to plug it into your calculator. And if you round it, probably round to the nearest hundredth, you get 1.414. If you're having issues with rounding, remember that I do believe it's page 23. Page 23 reviews rounding. Some of us are still getting that wrong. So go review rounding on page 23. So Pythagorean theorem is a nice way of finding the sides of a right triangle. It has nothing to do with angle measurements. It's nothing to do with the slope. It's finding the sides of right triangles and only of right triangles. Great application that you might use in your life. Good luck. Just for fun, let's do a bonus problem. Here I have x is equal to 1 plus 6 times the square root of the quantity x minus 9. Now remember, we're solving because there's an equal sign. And when we solve, we're supposed to isolate the radical, get this radical portion by itself. So in order to do that, the first thing we have to do is move terms over. So I'm going to subtract my 1. That's going to give me x minus 1 is equal to 6 square roots of x minus 9. Now technically, to get my radical isolated, the next thing I would have to do is divide by 6. But then I have to divide this whole thing by 6, which is going to make an ugly fraction, and I don't really like fractions. So I'm not going to do that. I'm going to hold it there, but I need to remember that it's 6 times that quantity. I'm going to go to my next step, which is to square both sides. I'm squaring this whole side, and I'm squaring this whole side. Now, on the left side, just as we did on that other problem, we need to remember that we cannot bring the 2 inside. The x minus 1 squared means x minus 1 times x minus 1. So we're going to actually have to FOIL that out. When we FOIL that out, we'll get x squared minus 2x plus 1. So your outside will give you a negative 1x, your inside gives you a negative 1x. That totals a negative 2x. And then negative 1 times a negative 1 gives you a positive 1. Now, on the other side, we need to make sure that we're paying attention to what's inside our parentheses. We have 6 times this quantity. This is a product inside here. Our laws of exponents say that if we have a product, the exponent can go on both of our factors. So that's going to be 6 squared, which is 36 times, and the square root here would cancel, leaving me this quantity of x minus 9. To indicate that it's a quantity, I must use my parentheses. So once again, the square went inside on both factors because they're being multiplied together. The square here gives me 36. Squaring this cancels each other, leaving me with the x minus 9. Have to take this 36 times this entire quantity, so we must have our parentheses. Now, in order to solve any equation, we can't have parentheses at this point. We have to get things all nice and pretty. So my next step is to eliminate parentheses by using my distributive property. Uh-oh. Let's see here. 324. Now, because I have an x squared, I know that I have to set my equation equal to 0. So that means I'm going to move everything onto this side because you always want to keep your x squared positive. So it's a positive 36x, so I'm going to subtract 36x. I'm going to line that right up underneath my other term with an x so that I have my like terms together. It's a negative 324, so I'm going to add 324 to both sides. They're both negative, so you add the number and keep the negative. They're both positive, so you add the numbers and keep it positive. Don't lose the equal sign. All that cancels out, leaving the number 0 behind. And now we have to factor. Fortunately, again, this is our easier type of quadratic because there's no number besides the 1 in front of that x squared. So we have x and x. It's a positive 325. Positive tells me both signs have to be the same because when I multiply the last, a positive times a positive is positive, or a negative times a negative is positive. It has to add to a negative, so both of them are going to be negative. And now I need two numbers that multiply to 325 but add to 38. Oh boy. Well, the first thing I think of is this ends in 25, which means that there's quarters in there. For every 100, that's 4 quarters, so 300, 3 times the 4, that's 12 quarters plus this 25, so that's 13 quarters. 13 and 25, hey, that's 38. So it's 13 and 25. And now that we have it in factored form equal to 0, we can set each factor separately equal to 0 and solve. X minus 13 equals 0, or x minus 25 equals 0. And then we solve by doing our inverse operation. Add 13 to get x by itself. X is the same thing as 13, or x is the same thing as 25. Remember, the key here is that we have to check our answers. Let's go to a new page. I'm just going to rewrite my equation on the new page. So we have x is equal to 1 plus 6 times the square root of x minus 9. And we have to check both of our answers. So the first one I'm going to check is x equals 13. All right, so wherever there's an x, I'm going to replace it with its equivalent value of 13. So it's going to be 13 is equal to 1 plus 6 times the square root of 13 minus 9. X is always 13 at a time. And now we just simplify using our order of operations. We do not do this addition first. 6 is being multiplied. Multiplication happens before addition in our order of operations. But that multiplication doesn't happen until we simplify underneath the square root. 13 minus 9. It's nice subtracting 9 from a teen number because you just add the two digits together. 13 minus 9 is 3 plus 1, or 4. Now we simplify the square root because remember, this is not the same type of number as the 6, so we have to simplify it to see if we can get it to be. The square root of 4 is 2, still multiplication. Once again, now multiplication is done before addition in our order of operations. So sure enough, 13 is equal to 13. So x equals 13 is one of our solutions. Now you cannot assume that 25 is not. So you still have to check it. Now these markers are a little bit thicker, so I seem to need more paper. Let's write that equation again. X is equal to 1 plus 6 times the square root of x minus 9. And now let's check when x is 25. Once again, wherever there's an x, I'm going to replace it with 25. Same first step, we need to simplify what's underneath that radical. So we have 25 is equal to 1 plus 6 times the square root of 25 minus 9. Once again, we can take away 10 and then add 1. It's 15 plus 1 is 16. Now we have to take the square root of that. The square root of 16, we said at the beginning, is 4, since 4 times 4 is 16. And now we have addition and multiplication. Order of operations says we do the multiplication first. Oh, look at that. That one checks too. So in this problem, both of our solutions check. So the solution to the answer to our equation is that x equals 13 or x is equal to 25. Bonus question number 2. Simplify the square root of x squared minus 10x plus 25. Here's a few things that we cannot do. Oh, there's a square here. Doesn't that cancel with the square root? No, this square is on this individual term. It's not on the entire quantity. You cannot take the square root of individual terms. Remember, our law says only if we were multiplying or dividing. Here, we're subtracting and adding. You cannot break that apart to separate ones. Oh, my all-time favorite. Oh, let me just square it to cancel out the square root. You said we could do that. We did that before when we were solving. Square, it gets rid of the square root. Let's think about that. If I square this, how does that keep the expression the same, or an equivalent expression? We squared before because there was an equal sign. When you have an equal sign, you have two sides that are in balance. And because you do something to one side, you do the same thing to the other side to keep it in balance and equivalent to each other. We do not have an equal sign here, so we can't just square to get rid of the square root. That would be changing the value of the problem. The problem isn't x squared minus 10x plus 25, it's the square root of that quantity. So you can't just make it go away because you don't like it. You have to make it go away legally. So you can't take the square root of individual terms. We can't just square it to make it go away. What can we do? Well, the first thing I see is that we have a trinomial. And no matter how badly you hate the F word, I think factor. We still have a square root. You can't get rid of that. But can I make this into two sets of parentheses? Well, let's see. This is the easy kind, so it's x and x. Need two numbers that multiply to 25 and add to negative 10. Well, it has to multiply to a positive, so the signs have to be the same. It has to add to negative, so they both have to be negative. Two numbers that multiply to 25, well, that's 5. 5 plus 5 is 10. So let's put the 5 in there. Okay, so it factors. Now, what do you notice about the factors? The factors are the things that are being multiplied together. So my factors are x minus 5 and x minus 5. What do we notice? They're the same. Anything that's multiplied by itself can be written as what? Anything multiplied by itself. Now don't lose the fact that you still have the square root. Anything multiplied by itself can be written as a square. So because these are the same, I can write that as a quantity squared. So x minus 5 quantity squared is the same thing as this trinomial of x squared minus 10x plus 25. So I didn't change the value of it, I changed what it looks like. And now I have a quantity squared that I'm taking the square root of. Now the 2 can cancel, leaving me with my base of x minus 5. Huh. Interesting how factoring keeps popping up. Use the tools that you know to work things through.